Bismillahirrahmanirrahim. Assalamu alaikum, everyone. Today we're going to finish up with lesson number 39, part 2. Just to remind you of what we did in part 1. Of course, you just did the homework, so you would know. But we learned to count, right? And that sounds kind of silly, like, okay, yeah, we've known how to count for so long until you do the homework for lesson number 39, and you're like, oh my God, counting is not the easiest thing in the world, right? And what makes it very difficult is where you start thinking about all the possibilities, right? When you think about all the possibilities, that's really where it gets kind of crazy. You're like, okay, I know how much more could possibly go on here. So what we're going to do today is actually extending that idea. We're taking that idea forward and very quickly counting is followed by probability. And if counting didn't get you, then probability generally does, right? These two go hand in hand. We teach counting first, and initially it doesn't seem like it's that confusing, but then it really starts to add up, right? So let's start with a few examples first, okay? Let's count the number of days of the week, all right? So very simple. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, right? We all know those. Now, if I told you count the days of the week, what you just did there is you told me that n is equal to 7. So please get used to this n. We refer to the count of something as n. And in our sample space, okay, so we have a new word now. It's called a sample space. In our sample space, which we call an S, of this situation that we're looking at, we have 7 days written out. So in the sample space, you write down what those things actually are, whereas the n value simply represents how many there are. You get it? So these are both, kinds of countings, really. All right, so the sample space is detailing for you what those 7 things are, whereas n is equal to 7 is just telling you the count of it, right? Now, I am wondering, right? I am wondering what is the probability, right? What is the probability that if it were to rain, if somebody tells me it's going to rain only on one day, okay, like they're telling me in advance, it's only going to rain one of the days. So I'm looking for the probability that it rains only on one of the days, right? None of the other days, just one day, right? Now you might be going like, wait, which day is it? That's the thing. You don't say which day is it. That's a broken question. In probability, you don't know which day it is. You're looking for the chances of it being a given day. So let's suppose you're like, well, is it going to be Monday? I'm going to be like, I don't know. I just told you I don't know, right? But what I can do for you is I can give you a chance of what are the chances that it would be Monday, right? And you've been doing this your whole life, right? What are the chances of being of Monday? Well, you're going to say, well, how many days are there? There's 7 days of the week. So you'll say, well, if you're telling me it's only going to rain on one day, then the chances of it being on Monday is going to be 1 out of 7. The chances of it being a Tuesday is going to be 1 out of 7. The chances of it being a Wednesday is 1 out of 7. Right? So we very quickly turned that rains only one day into Monday, right? But basically the idea was every one of these is going to be 1 out of 7. And if you add up all the probabilities, the 1 out of 7 plus the 1 out of 7, and you do this how many times? You're going to be like, well, I have to do this 7 times, right? You do this 7 times. And so you're going to end up with the answer 1. So you always have the same value. It's always going to add up to 1. The probability is always going to add up to 1, all right? So all of a sudden, what was a counting problem can be turned into a probability problem. It all depends on the question that you have been asked, all right? Now, let's suppose that we're talking about a particular candy, And let's suppose that particular candy has pieces that come in red, in yellow, in green, in orange, and I can't really remember Skittles, but I did this lab some years ago with my students, and it's just not coming to me. I think it's like violet, meaning purple. That's why they call it Taste the Colors of the Rainbow. But anyway, you're better at this. I don't really eat candy, but let's suppose that this is a candy. All right, this is the candy, and these are the 5 colors that the candy has. Well, guess what? Now this becomes my sample space. All right. There's reds, there's yellows, there's greens, there's oranges, and there is purples. Now, what if the manufacturer tells us that we've got in here, we've got 10 reds, we've got 5 yellows, we've got 4 greens, we've got 10 oranges, and we've got, let me put OR there, and 7 purples, right? I just want you to think to yourself, how is this not like that probability of a raining on a day example, right? Before, there was 1/7 chance, equal chances to be on a certain day. This is not equal chances. So let's suppose, we all do this. We open up a packet going like, man, I just want the red ones because they taste the best, right? So I am looking for the probability that I pick out one piece of candy, even though that's not enough, but one piece of candy, and I'm looking for it to be red. I'm only interested in being red. Well, then you would say, let's count up the sample space. And the sample space is not 5. You really realize that. There's 10 of the red, so 10 plus 5 is 15, plus 4 is 19. 19 plus 10 is 29. 29 plus 7 is 36. So there's really 36 overall. Now, how many of these happen to be red? There's 10 of them that are red. And because 10 of them that are red, that means 10 divided by 36 is going to give you 5/18. So there's 5 chances out of every, there's 5 chances out of every 18 chances that, or just say 18, 5 chances out of every 18 that I'm going to end up with a red. You understand what I'm saying? So what students generally get confused by, and the ACT really banks on this, right? They think that, well, if you're talking about one piece of candy, there's one, you're trying to take out 1 out of 10 reds. This is the wrong understanding of it. That's not how probability works. We're saying out of the entire bag of candy, we're looking for one of those pieces of candy to be red. And so that is the chance that we have for that to occur. What if you said, all right, I want 2 pieces of candy? Well, I'm going to ask you this. Are you looking for 2 pieces of candy as in you're going to pick them both out at the same time? Or are you looking in 2 pieces of candy in that you're going to pick one and then you're going to pick the next one? Okay, so if you're looking for the probability that your first piece is red, okay, and then you're looking for the probability that the second piece is, actually, you know what, let's pick a different color. Let's say yellow, right? You're looking for this probability to occur, right? Where you don't replace them. You pick out the first piece and then you pick out the second piece. All right. So what might this actually end up looking like? I realize you want 2 things to occur. You're asking for a lot. Okay. So let's see here. Let's talk about the probability of the first piece being red, right? So the probability that the first piece is red is really no different than the probability over here, right? The probability over here for the first piece being red was 10 out of 36. There were 36 pieces of candy, 10 of them being red. There was 10 chances out of 36 for that to occur. But then you're saying that you want the second one to occur as well. So you're implying that you want one thing to occur and the other thing to occur. In probability, the word "and" is a very powerful word. It means you need multiplication. you need to multiply the probabilities, because you're adding, you're not adding, you're multiplying all the possibilities that could occur. So when you say you want the second piece to be yellow, first realize that you already took one piece of candy out of the bag. So now you only have 35 pieces of candy. But my question to you is, how many of those pieces of candy are yellow? 5 of them are yellow, right? So 5 out of 35. So really what this problem becomes is, it becomes 10 over 36 multiplied by 5 over 35. And that's a pretty small number, right? That's going to give you, without simplifying things, because I do want you to just kind of look at the fractions and kind of get used to them. So you have 10 divided by 36, and you're multiplying that to 5 divided by 35. So I'm putting parentheses around that second one so you don't get confused by it. And that gives you 0.039. 0.039. Or if you want to turn it a percentage, 3.9%. So that's the amount of chance that you have of something like that occurring. See, as a statistician, I'm not telling you what's going to occur. I'm telling you what are the chances what you're looking for is going to occur. You see that, right? Now, what if you said that I'm looking for the same exact probability, but this time what I'm going to do is I'm going to just go ahead and try to pick both of them out, where I pick out the first piece. Okay, first piece is red, so that's the same thing as before. And then with replacement, right? So you put the first piece back with replacement. So you replace it this time, and then you're going to look for the second piece is yellow. Second piece is yellow. Now what's going to happen? Well, when you're looking for the first piece being red, it's still 10 out of 36. There are 10 pieces that are red out of 36 pieces in that bag. But when you replaced it back, whatever you got, you put it back into the bag. Well, now you have 36 in the bag, you realize, not 35 anymore. But how many yellows are there? There's 5 still yellows that are in that bag. So you're looking for both of these to occur, so you're still multiplying, okay? You're still multiplying 10 out of 36 multiplied by 5 out of 36, and that's going to give you something that's probably a slightly higher probability, because now, or maybe not a higher probability, but let me not take guesses. Let's just go ahead and try it first. So 5 out of 36, and you end up with 3.8%. So 0.038, 3.8%. And you're wondering, like, wait, why is it not a higher probability? It's because, just think about it, the chances of you now getting a yellow with there being more pieces in that bag again, slightly more pieces, like one more piece as opposed to before, automatically, before there was 35, now there's 36, you have less chances of getting that yellow that you're really looking for. Right? So this topic is really vast, and it's a tough topic. And if you can understand this, a lot of things like the lottery, gambling, things like that, they make a lot of sense to you as to why we've been recommended to stay away from such things like that as well. Okay. Now, we're going to do a little experiment, and much of the lesson I don't plan on actually writing much. I know that I've started the lesson with writing, but it's not going to be a whole lot as I write here. So let's suppose that I had a coin, okay? And basically, I'm just going to tell this computer to toss the coin. Let's suppose I tell it to toss it once. So it'll toss that coin for me, and once it tosses that coin, it's going to tell me what it got. So it got a head, right? It got a head. And then I press it toss again, it tosses that coin again, and it gets a head. And then I tell it to toss again, and it tells me that this time you got a head. So think about it. How many sides of a coin there are? There's 2 sides of a coin. So wouldn't you have expected that there would be a tails somewhere? And you still haven't gotten a tails, right? So look at that. 4 heads altogether, right? 4 heads. And you might be wondering, what's the purpose of doing something like that? Well, there's our tail. Look, according to the experiment that we're doing, we're running an experiment. Some people call it a simulation. What we're learning from this is, listen, just because one side is a head, one side is a tail, does not necessarily mean that they're going to be equally proportioned out, right? So in this case, I flipped the coin 8 times, and look at that. This is totally random. 4 heads and 4 tails. But if I had looked on the fourth toss, I would have been like, this isn't working out for me, right? So here are 10 tosses, right? I believe I've tossed it 10 times. Notice in 10 times, I've got 11 times, sorry. I've got 6 times that it was head and 5 times that it was tail, right? And we've done this in real life with our students, and sometimes you really cannot get the numbers you're looking for. So what if you were to toss this 1,000 times, right? Like, let's suppose you decide to toss this coin 1,000 times. So this thing will toss it for us 1,000 times, and it'll give us a list. So here's a list, and obviously we're not going to read through the list, but there's the list of what we got, right? And then if we were to look at the table tells us that there was 488 heads and 512 tails. So it's a little bit lopsided, and the ratio is still not 50-50. So this is called experimental results. These are experimental probabilities, right? But what do we know? What do we know from our understanding of probability, the chances of getting a fair coin? This is called the theoretical probability, right? So the theoretical probability, basically this one is telling you before you even start, what are the chances of something happening? And the chances of something happening like that, the probability of getting a heads was equal to 1 over 2, and the probability of getting a tails was equal to 1 over 2. Whereas the experimental probability that we carried out, right, we ended up with, how many heads did we have? We had 488 heads out of 1,000. So that was 488 out of 1,000. That was the probability that we got for heads. And then 512 out of 1,000 is the probability that we got for tails. So you might say, wait a minute, then that means the theoretical is all wrong and it's the experimental that really works. Well, you know what? Because I am a stats major, I'm going to tell you something here. Basically, so much of statistics is knowing the answer. You know it's going to rain, sort of a thing, right? But then you keep experimenting with it. You keep experimenting with it until the two match, right? So there's a theorem, and I don't want to go too well into this lesson, but if you're interested to know, there's a theorem that says, well, technically speaking, all right, it's called the central limit theorem in statistics. If you continue to toss this coin infinite number of times, not just 3,000 times or 4,000 times, we're talking until infinity, right? So not even 1,000,000, not even 2,000,000, just forever you continue to toss this coin, what you will discover is the proportion of heads to the proportion of tails is going to become 50-50. No matter how you slice it, it's going to be that. You can already see that it's approaching. There's 0.499 and 0.500. So it just boggles the mind. Like, how can that possibly be? But that's a fair coin, and that is what we expected. So eventually that experiment will turn into what your expectation is going to be. But you have to experiment many days, right? Sorry, for many of those tosses. Now, the next set here says you have a bag of M&Ms, and they're colored red, green, blue, brown, yellow, and orange. So I did Skittles with you earlier, what I thought was Skittles, and this is M&Ms. And it says determine which of the following are probability models. So a probability model is going to be only something that needs to add up to 1. So the addition of all of the probabilities needs to equal 1. Remember, this was the addition sign. So if you add up all the probabilities, they need to add up everything equal to 1. So you basically look through these charts, and if they don't add up to 1, then they don't work. All right? That's one thing. And the second thing to mention is probabilities cannot be negative. Okay, so they always have to be greater than or equal to 0. A probability cannot be negative, and the summation of all the probabilities needs to equal 1. So for instance, what's wrong with diagram C? In diagram C, you've got a negative sitting right there. You can't have a negative probability. So that's not a valid probability model, right? The question says determine which of these are valid probability models. Then you want to just add up these numbers over here. If these numbers add up to exactly 1, that's a valid probability model. If they don't add up to 1, then it's not a valid probability model. By the way, look at letter D. There's nothing wrong with that, by the way. I know it seems awkward, but it's still a valid probability model because it fulfills both the conditions that we're referring to. All right, now we're going to talk about a famous problem, and I tried to avoid the famous problems, and I tried to go with something that was just off the top of my mind because I'm looking outside and it's raining, so I was like, let me talk about that. Here is basically what we're looking at now. We have a fair die. If you don't know what a fair die is, there's a difference between a fair die and a loaded die. A fair die, all right, a fair die basically means that every side has an equal chance of being reached. Okay, so if you flip a coin, there is exactly 1 chance out of 6 that you're going to get the number 1. 1 chance out of 6 that you'll get the number 2, like that. That's called a fair die. If it's a loaded die, because this is in your homework, so you might be like, what does this mean? What is a loaded? So when something is loaded, right, when something is loaded, basically not every side has an equal chance of being reached, right? And so it could be possible that somebody shifted the weight inside of the dice. And yes, you can do that. Inside of the die, you can shift the weight so that the number 3 doesn't really show up much. So one of the reasons, one of the things that they need to watch out for in things like casinos and stuff like that where die are used all the time is they got to make sure that the die are like, you know how when you have a professional basketball game, they have like the best basketball. So in this, they have like the best die that was ever made, and then they use that. So it's got to be exactly perfect weight for you to like gamble. I mean, I'm not telling you to gamble, nor have I gambled, but I'm just saying that that's a thing, right? So it says an experiment consists of rolling a fair die once. So you're only rolling this thing once. A die is a cube with each face having either 1, 2, 3, 4, 5, or 6 dots on it. So we know that, and of course we see it in the figure. It says construct a probability model for this experiment. So again, a probability model basically begins with you writing down a sample space. You begin by saying that it could be a 1, it could be a 2, it could be a 3, a 4, a 5, or a 6. Okay? Now a probability model is like the one that you just saw earlier in these tables over here, where you write down outcome and you write down probability. All right, so you make a little table. I know it's kind of redundant, but it's better to start with a simple example than to just kind of speed forward to a very difficult example and everyone's just kind of confused, right? And we don't have the chance for you to ask me questions, subhanAllah. So the chances of you having a 1, 2, 3, 4, 5, 6. Notice how this essentially is your sample space. All right, that's your sample space right there. Now you just got to ask yourself, what are the chances of you getting a 1? Well, that's 1 out of 6 chances. 2, 1 out of 6. 3, 1 out of 6. 4, 1 out of 6. So like this, each one of these is 1 out of 6. And if you want to make sure that it's a valid probability model, add all of those probabilities. Do you end up with a 1? Yes, you do. And is each one of those probabilities a positive, right? Every single probability, is it greater than or equal to 0? Yes, it is. So you made a valid probability model. So this is called the probability model. That's what a probability model looks like, okay? Now, what if this was a loaded die, right? What if this was a loaded die? Well, let's suppose that in this, now you kind of get to pick the numbers here. So let's suppose that we're looking at an outcome and we're looking at a probability, right? So we cheat and we somehow make this die so that it's heavier on the 3 side than the other side. So here you go, 1, 2, 3, 4, 5, 6. And we cheat and we make it so that the chances of you getting a 3 are, let's suppose, 3 chances out of 6. All right? And the chances of you getting a 1 are 0 out of 6. The chances of you getting a 2 are 0 out of 6. The chances of you getting a 4 is 1 out of 6. The chances of you getting a 5 is 1 out of 6. And the chances of you getting a 6 is, bismillah, is 0 out of 6. All right? Is this a valid probability model, though? Yes, it is. If you add up all the probabilities, you'll end up with 1. 3 plus 1 plus 1. Oops, sorry, that's not valid probability model. Let's change one of these numbers. I apologize. And there you go, 1 out of 6, and now it's a valid probability model. So these do add up to 1. And then, are each one of them greater than or equal to 0? Yes, they are. So this is a valid probability model. So that's a loaded or a weighted die. Another way, and a cheaper way to cheat is, I know I'm talking about cheating here, but basically, a lot of gambling and stuff like that, much of the application is about how to beat the game. And in a sense, sometimes you have to cheat the game to beat the game. What if you had one side, right? If you don't understand loaded die, let's just suppose that you actually had one side that actually had a 6 and another side that had a 6, right? So for instance, in this situation, if you're looking at outcome and you're looking at probabilities, right? In this situation over here, what's going on is the chance of a 1, 2, 3, 4, 5, and 6. But in this situation, maybe you took off one of the sides. Let's suppose you took off the side that had the 1 dot and you replaced it. Or let's say the side that had the 3 dots, right? So the side with the 3, you replaced it with the side with the 6. So there's 0 out of 6 chances of that happening, but there's 2 chances out of 6 of a 6 occurring, like that, right? And the rest of them are standard at 1 out of 6 each, like that. Same question, is this a valid probability model? Yes, all the probabilities do add up to 1. Is each probability greater than or equal to 0? Yes, it is. So again, this works out for you, okay? Now, I just want to officially share with you the formula for probability, just in case there's something that I missed out. But basically, the book says that the probability of an event, right? When you're looking for something, we call that, this is important, this is called an event. It could be anything. Like, for instance, earlier when I did the example about the rain, the event was it raining on a day. When I did the example of, Bismillah, of getting a red, right? When I did the example of getting a red, that was the event for getting a red, like that. Okay, so different events can occur. It's just, depending on what they're talking about. But what it says that the chances or the probability of an event occurring is equal to the number of ways that it can occur divided by the number of possible outcomes. All right, so that formula is rather vague, and I'll be sharing with you how this formula applies, and that's what's the most important. Okay, so let's go ahead and try a few examples here. It says calculate the probability that in a 3-child family there are 2 boys and 1 girl. Okay, now first thing that we got to do is write what we're looking for. Okay, we're looking for the probability that we have in a 3-child family that there are 2 boys, all right, there are 2 boys and 1 girl. Now notice how that's kind of annoying to write so much stuff into like a parenthesis, right? So that's why we define events, right? We'll call this event, let's call it event E, right? So now we can just keep writing down the probability of E occurring, and if somebody says, what is exactly E? Then you can tell them, I'm looking for the probability of getting 2 boys and a girl, okay? All right, now it says assume equally likely outcomes, all right? So it's equal chances of this couple having a boy or a girl, right? So half and half, inshallah. All right, now what the first thing you got to think about is the sample space. What are all the possible outcomes? Now, initially what students think, right, and even adults, they're like, wait, so there's only two possible outcomes. What's the big deal, right? There's only a boy or girl. No, we're saying in a 3-child family where one child occurs after the other, right? So you've got the first child, all right? So you got child number 1. The first child could be a boy or they could be a girl. All right, so the first child is either a boy or a girl. We're looking at the first child here. But then the second child realized when when that couple has a boy, that second child could again be either a boy or a girl. So now to that one event, to that one chance, there are two separate chances. And if they had had a girl, then they could still have a boy or they could have a girl. What are we really starting off this problem with? Have you realized we're really starting off with counting? Remember when I started the lecture, I said probability really starts from counting, and usually when students struggle with probability, it's because they did not spend proper time in learning to count, right? And so you got to go backwards and be like, okay, let's figure out the count then, right? So now in this situation, what's really happening is this. Look, you don't have to make this tree diagram. You really don't. Okay, this is just a demonstrative thing, and I only brought it in just to show it to you, right? I didn't need the tree diagram. I can tell you that, look, if there's a first child, that's 2 possibilities, right? Then there's a second child, there's 2 more possibilities. But I'm going to have to multiply them because that's what the counting principle said in the previous lesson, all right? Then that third child, there's 2 more possibilities. So altogether, you should have 8 possibilities. I could have counted that out for you. So here is all of those 8 possibilities. Then why exactly do we even have to write all that out? It's because if I ask you, yeah, the number is not enough for me, I need, well, that's a horrible parenthesis, sorry. I need the sample space, then you got to sit there doing this. You got to say, well, in the sample space, there's a boy, boy, and a boy. Then there's a boy, boy, and a girl. Then there could be a boy, then a girl, then a boy. Then there could be a boy, a girl, then a girl. Then there could be a girl followed by a boy, followed by a boy. Then there could be girl followed by a boy, followed by a girl. Oops, sorry. And then there could be girl, girl, boy. And then there could be girl, girl, girl. Okay. Now, what was the question? The question was, what are the chances that you have 2 boys and 1 girl? Okay, now let's go to our sample space. We're looking for the probability of E, where you have 2 boys and 1 girl. Remember, you have 8 possible outcomes. That's the sample space of all the possibilities that could possibly occur, right? How many of these have 2 boys and 1 girl? Here is the first one. 2 boys, then followed by a girl. Here is boy, girl. I was going to say burl. So boy, girl, boy. That works out for us. Girl, boy, boy. That one works out for us. And you want to look carefully. Is there any other way that this could occur? No, there is not. So there are 3 chances out of 8 that this couple has 2 boys and 1 girl, like that. Okay? And continue to kind of think about that idea. It's not the simplest thing to do. It takes a while, but I am telling you right now, usually what it really results from is students not understanding how to set up a sample space. So whenever you're stuck with probabilities, some of those homework questions are insane. The sample space is like 48, so you need to think of like different techniques to prevent yourself from making 48 things. But there you go. Once I made the sample space, it was quite simple to tell what are the chances or what's the probability of having in a 3-child family 2 boys and a girl. Okay, I have a couple more things to show you, and then we'll inshallah wrap up. One of the reasons why I'm trying to wrap this up as much as possible is because Ramadan is about to start, so I really want to, I'm sure when you watch this video, Ramadan will be well on its way, but you know, Ramadan starts tonight for many of us, so we got to make sure. I just, you know, trying to clear my schedule out, sort of a thing. All right, so it says consider the experiment of rolling a single fair die. So I hope that you know what a fair die is now, right? It says let E represent the event roll an odd number. So let's pause here. What are all the odd numbers on a bismillah, on a die, right? And we'll call that event E. Okay, so event E could be a 1, it could be a 3, or it could be a 5. And what is the count of event E? The count of event E is 3. There's 3 possibilities, right? Now let's take F. And F represents the event roll a 1 or a 2, meaning it's telling you it's got to be a 1 or a 2. Well, what's the count of this event? There's 2. All right, that's a count of 2. Now, it says write the event E and F. What is the intersection? What is the count of E and F? Now, this looks very, very confusing. It sounds confusing. Look, let me just make very good sense of it for you, okay? You're looking, remember from that previous section, and means both things occur, right? All those Venn diagrams, that's why we made them. But, you know, it just seems like it's irrelevant right now. You're looking for something that, so you roll a die and you're looking for what's the number where you can roll an odd number and you can have a 1 or a 2. Now, 2 is not an odd number, right? But 1 is an odd number. So what I'm trying to say here is you could just say, look, that count for E and F occurring. Remember, it's the count. It's the count, not the number itself, just the count. The count of numbers that can do that is 1. There's only one situation, and I can highlight that for you. Event E has a 1, and event F has a 1. So the event that you roll an odd number, okay, could be 1, 3, and 5. The event that you roll a 1 or a 2 is obviously 1 or 2. But how many of them have such that you have an odd number and you have a 1 or a 2? There's only one way that could happen. So there's only one count that'll work for us. Letter B. It says that write the event E or F. Now, this one gets a little bit trickier because when they say E or F, you want to prevent from double counting. Remember that, right? So if it helps, you know there's an overlap. All right, here's E, here's F. E has all of these numbers in it. It's got a 1, it's got a 3, and it's got a 5. This is for the sample space, by the way. And I'm sorry if I'm confusing you. This is not counting in the sense that you're putting in how many possibilities. You're putting in what are the possibilities. So E could be 1, 3, or 5, right? And F could be 1 or 2, right? So F can be 1 or 2. And what did I just say? The count of where E and F both occur, there's only one number that does that, and that's the number 1. Okay, so there's only one number that does that, it's the number 1. Now, what is the count of having a number in E or F? Meaning you end up with a roll that is an odd number or a roll that's 1 or 2. So in that situation, you have to be careful of double counting. Remember, here's 2 possibilities. Here is another possibility. Here's another possibility. So the answer to this is 4. There are 4 such ways that can actually happen. All right, where you end up with a odd number or you end up with a 1 or a 2. Now, that question, it's a little confusing and it's even hard to explain until you don't get to probabilities. Now, probability of E is what? You're looking for the probability that you end up with a dice, so you end up with a roll. You roll a single fair die, just once, single. You roll an odd number. So think about it. What are the chances out of 6 chances in a die that you end up with an odd number? There's 3 chances that would occur, right? And so you would say that you have half the chance of that actually occurring for you. Now, if you want to use the formula, by all means, you can take a look at the formula and read up on it and say, okay, I'm going to use the formula to do this problem. But I would really recommend that you just kind of stick to what I'm saying here, because the formula says the count of E occurring over the count of the sample space, and that's just enough to confuse anybody. Turn a simple problem into a difficult problem, kind of like how letter A and B were, right? Now it says compute probability of F, meaning what are the chances that you roll a die and you get a 1 or a 2? Well, automatically you'll say, well, there's two sides that are 1 and 2, and so there you go, 2 out of 6. So there's a third of a chance that you end up with a 1 or a 2 on a roll. Simple, right? Letter D, it says, what is the probability that you get E and you get F to both occur? Now, recall what we had initially said. What is E and F? E and F is the ways that you can end up with an odd number, right? And you end up with a 1 or a 2. Well, we said that there's only one way that can possibly occur, and there's 6 choices. So 1 out of 6 is really what we're looking for. And that right there gets a little confusing for students. They're like, wait, how did that occur? Again, if you just kind of list it out for yourself in different sorts of ways, you'll understand that there's 1 in 5 chances. Okay, there's 1 in 6 chances that would actually occur for you. Okay, now let's do letter E. Letter E says probability of E or F. Again, learn what E and F are first, right? E, for the last time, was rolling an odd number. So that's a 1, 3, or a 5. And F was rolling a 1 or a 2. So the probability of either rolling a 1, a 3, a 5, or a 1 or a 2. Now notice how the 1s got repeated. This is what I was trying to explain to you earlier, right? So really you're looking for a 1, a 2, a 3, and a 5. When you account for all that, you say, look, you're just saying that I'm looking for a 1, 2, 3, or 5. Just say that, right? So there's 4 choices, there's 4 chances out of 6 that would actually occur for you. That simplifies to 2/3. So there's 2/3 for every, you have 2 chances out of every 3 for you to get what you're looking for over there. Okay, now the last thing that I want to work with here is spinners, because I've discovered that students, they initially knew about spinners. I actually was one of the students that I actually had no idea what a spinner was, believe it or not, even as a teacher. It was only when I'm like, what in the world is this? And I believe it or not, I saw it in a kindergarten book and I'm like, what? What's this? So I must have missed that. So maybe you missed it. Maybe you were you were having that situation. So I want to just kind of talk about this. First off, it says use the following spinners to construct a probability model for each experiment. And so these can take a little bit of time, right? So let's go ahead and read one of these. It says spin spinner 3. So here's spinner 3, all right? Then spinner 2. So you spin spinner 3. That's like a tongue twister right there. Now, here's spinner 3. Okay, here's the first thing that we're doing. We're spinning spinner 3. They could have made this easier by, I don't know why they couldn't. So, there it is. So you spin spinner 3. That's the first thing that you do. Then you spin. So it's like first child, second child, right? Even though it's not having children here, but it's just how it looks right now, right? So spinner 3, then spinner 2. Well, let's talk about the possibilities for spinner 3. So you start off with the dot and you say, look, you can either end up with forward or you can end up with backward, like that. Okay, so there is your 2 possibilities right now. All right. Then it says that after you have spun spinner 3, then spin spinner 2, then spin spinner 2. So that's going to give you, I'm sorry, so red, yellow, and green, right? So red, yellow, and green. So R, Y, G, and same thing over here, R, and then Y, and then G, right? So altogether, what you really have is this occurring is you could have forward and then R. You could have forward and then yellow. You could have forward and then green. You could have backwards red, backwards yellow, and backwards green. So what is our sample space? Our sample space is right over here, right? Our sample space is right over here. Now don't get confused by how I made the diagram. Some people like to write down first and then they put down F on top of this. Okay, so don't worry about that stuff. Just however it makes sense to you. Like for instance, the way that the book did it is it just made these trees. It didn't put letters in the middle. And I imagine this is probably a better way to do it, but I'm not going to go back and change it now. So they did first child, second child. So first spin, second spin like that, okay? But regardless of how you make this, here's our sample space. Now, it says, what is the probability of getting forward followed by yellow or green? So here goes. The probability of that happening is going to be, Bismillah, yeah, so you're looking for forward, so that's only these three chances right here, followed by yellow or green, so that's two of those 6 chances that you have. So 2 out of 6 chances, i.e. 1/3, is the probability right there. You see how I did that? Okay. Now in this next diagram that I make, I'm going to try to stick to the way that they did it. I don't want to confuse you with 2 different stories, and I apologize for that, right? So number 20. All right, actually, I think I'm going to need a little bit more space because I've already taken up a lot of that space to do this. So, okay, I'm running into a boundary here. Let's go here. Okay. So in number 20, it says spinner 2, then 1, then 3. Okay, so 2, then 1, then 3. So I'm going to go ahead and designate these. This is 2, this is 1, and then this is 3. All right. Hopefully this goes a little bit better for us, the way I write it. So let's start off with spinning 2. So if we spin 2, all right, so there's 3 possibilities when we spin 2. And then I'm not going to write these here. I'm just going to make notches, all right? And those would be red, yellow, and green. Okay, so R, Y, G. And there's equal chances of that occurring, right? Equal chances. That's what the areas represent. 3 equal areas. Then it says that, again, we're doing number 20 in case you lost track, or more than I lost track. So then 1, then 3. So then look at the possibilities of 1. So if you're talking about the possibilities of 1, that could be that each one of these leads to 2 possibilities, and those 2 possibilities are obviously forward, oops, sorry, that looks like an R, forward, then backward, forward, then backward, forward, then backward, like this, okay? And finally, it says, then you're going to spin, 1, okay, I apologize. So there you go, I messed it up. So if we're talking about 1, that's not forward and backward. 1 is this guy over here. So 1 has 4 possibilities. I do certainly apologize for that. It's the kids making noises and stuff like that. That just kind of throws me off. So there you go. So there's 4 possibilities. 1, 2, 3, and 4. 1, 2, 3, and 4. So now you have 4 possibilities to each one of those. And we're really quickly going to number these. I think in me doing this example, you're probably like, okay, I got this already. But, for sake of completion, 1, 2, 3, and 4, like that. Okay? And then finally, it says spinner 3 in number 20. Okay? So when you spin spinner 3 in number 20, that's 2 possibilities. So I'm going to make to each one of these 2 possibilities. So 1, 2, 1, 2. And you're getting how we're doing this, right? Every single time. So like this, you continue that, and you come up with these combinations, right? you come up with that first combination. What's that first combination is going to be? It's going to be a red followed by the number 1 followed by a forward, right? So the number 1 and then forward. Okay, what about the next one? That would be red followed by the number 2, right? Followed by, or actually no, not 2, 1 and then followed by backward, like that, right? So like this, you can list out all those possibilities. But one thing I will tell you, as far as counts are concerned, I could have done that from the beginning. There's 3 chances for 2, spinner 2, then there's 4 chances for spinner 1, then there's 2 chances for spinner 3. Now remember, in the homework, you need to write out all those chances. That's called sample space. And I know it's a lot of work, but you need to do it, though. That's the only way you'll learn, right? So there's 24 such possible outcomes that you'll have to enumerate. After you have written out those possible outcomes, then and only then can you solve this question that it's going to ask you, what is the probability of getting yellow followed by a 2 or a 4, right? So followed by forward. So we're looking for the following to occur. We're looking for a yellow, then a 2, all right, then a forward. Or we're looking for a yellow followed by a 4, then a forward. So you know that these are 2 unique possibilities. Those are 2 unique possibilities. Out of how many possibilities? 24 possibilities. So that's 2 chances out of 24 of that occurring. And if you realize, wait a minute, you didn't even need to do the diagram to do it. I realize that, okay? But I need you to understand this situation really well. And for that, I need those diagrams from you. You don't have to do it for anything that's past 24, though. I know that I think in the homework there's something that has like 48 possibilities. So please don't draw out all 48 possible chances. But this one, 24, is not a difficult number, okay? So sorry about the few mistakes and stuff like that in this lesson, subhanAllah. But good luck to you in doing your homework. And I know it's a very different one. Feel free to reach out if you don't understand. I'll try my best to help you guys out, inshallah. And good luck and assalamu alaikum.